The big idea here is that naming and formula writing has certain strategies to them. Now, if you have time, please check out this video by Tom Lehrer, The Elements. It's a classic song in which Tom Lehrer, a musical comedian, was able to turn the elements into a song. In addition, I want you, if you can, also check out what dihydrogen monoxide is. It's a pretty interesting compound. You might even know what it is, but definitely go check that out as well. So our first thing we're going to talk about is, where do element symbols come from? Because a lot of times when we talk about elemental symbols, we see that most of the time it comes from the first letters of its name. So an example that would be, for example, carbon is C, or for example, lithium is Li. But others come from their Greek or Latin origins. Okay, and examples of that would be, for example, iron is not IR, it's Fe for ferrous. Sodium is Na. In addition to the first point when we talk about first letter of his name, if the second letter is taken, for example, then they'll use a third or fourth letter. Like such as, for example, if we talk about, for example, manganese. Manganese is Mn, so the first and third letter. What we just have to know is that the first letter is always capitalized, the second letter is always lowercase. So now we're going to talk about what are ionic compounds. Ionic compounds are elements made up of, or compounds made up of, metals and nonmetals. Okay. And we know what the metals are because metals, if I open up my periodic table, metals are found on the left side of the periodic table. So the left side of the periodic table are the metals. The right side, where there's a staircase, are nonmetals. So that's what we have here. Now, we also know that all metals are positive ions, while all nonmetals are negative ions. These positive ions are called cations, while these negative ions are called anions. We also have elements that hug the staircase, which we call the semimetals or metalloids. And then last but not least, these metals right here are called the transition or the multivalents because they have multiple charges. So this is what we have with regards to the periodic table. Now the last thing we have is that these elements, the lanthanides and actinides, actually fit in right here. That's why you go 57 jumps to 72. It's because this section actually fits in here, and this other section fits in here, but they are in a separate section because of something called its orbitals. So we have, in this case, metals turns into positive ions because they give away electrons. And when that happens, we call these a cation. While nonmetals are negative ions because they gain electrons, and thus they're called anions. Okay, so again, metals are found on the left side, nonmetals are found on the right side. All right, so here are some terms that we should definitely know that are important for us to know whenever we come across them. Okay, so the first term we should always know is monatomic. Monatomic comes from the word mono, which is one. It's one atom. So for example, iron. Iron could be one atom. Gold could be one atom. Okay. We also have diatomic. Now, coming from that name, then diatomic is two atoms. Such as, for example, oxygen is diatomic. Carbon monoxide is diatomic. Sodium chloride is diatomic. We of course also have triatomic, which is three atoms. And then lastly, we have polyatomics, which is many atoms. Okay, and you might have heard of the polyatomics before as the polyatomic ions. Those are ions made up of multiple atoms. So now what we're going to go into is how do we write the chemical formulas of non-multivalent ionic compounds. So this is the easy part of this lesson. Remember, the first thing is metal symbol always comes first. Okay. So what you want to do, first step, write element and charge as a superscript. So superscript just means like an exponent. The charge will be written like an exponent. Okay. Step 2. Balance charge by finding LCM. So what that means is because compounds are neutral, you gotta make sure the positive charge and negative charge balances out by having multiple of that element. Okay, you want to have multiple of that element. Number 3. Multiply each element until charge is LCM. So you want to multiply each element until its charge reaches the LCM. Number 4. The number of multiples is written after each element as a subscript, so below now. So finally, your compound should be neutral. You don't have to write any subscript of 1, so if there's only one element, you can ignore the 1. So that's what we have here. So let's take a look at our first example, potassium oxide. So if you look at potassium oxide, on the periodic table, potassium is right here, oxygen is right here. Now, how do you remember the charge of each of these elements? Well, how you remember the charge of each of these elements is based on the columns. Column number 1 elements are all positive 1 charge. So if you want to write this down on your periodic table, that's really helpful. Column number 2 is all positive 2 charges. These are transition metals, so they have multiple charges. We'll find out how to deal with them when we get to that section of our notes. These ones all have positive 3 charge. Over here, these are noble gases. They have no charge or 0 charge. The halogens, which is column number 17, are all negative 1 charge. So fluorine has negative 1, chlorine is negative 1. Oxygen's column is negative 2 charge, so these are all negative 2. Nitrogen's column is all negative 3, and then carbon is actually plus or minus 4. So that's how we figure out what the charge of each of these are. So look at potassium. Potassium is positive 1. Oxygen is negative 2. So we have potassium positive 1. Oxygen negative 2. So now we have two different charges. If they were joined together just like this, they will be an unequal balance of charges. So we gotta make sure they're balanced. So we look at the LCM. What is the LCM of the number 1 and 2? And the number is 2, which means that I gotta multiply potassium by 2 to become a positive 2 charge in a sense. So you need 2 potassiums to become positive 2. How many oxygens do you need to become 2? You just need 1 oxygen. So now these multiples here can be written as subscripts. So what you have is you have 2 potassiums, you write as K2, and oxygen is 1, but you don't have to write 1. It's K2O. And because it's 2 potassiums and there's 1 oxygen, these are now balanced in terms of their charge. So that's how you work on the first example. If you look at the next one, magnesium phosphide. Magnesium is Mg. The charge of magnesium being on the column number 2 is positive 2. So it's positive 2. Phosphide is phosphorus. Phosphorus is underneath nitrogen. Nitrogen's column is negative 3. So P minus 3. So what's the LCM of 2 and 3? Lowest common multiple of 2 and 3? It's number 6. So what we have here is we need to have 3 magnesium and 2 phosphorus to make them balanced. So what we end up with, we have Mg3P2. Our last example here is barium fluoride. Barium is right here. Okay, so because of that, barium has a +2 charge. So barium has a +2 charge. Fluorine is F. It has a -1 charge. So again, LCM of 2 and 1 is 2. So what we end up here is we need 1 barium and 2 fluorines. So we end up with BaF2. Okay. What happens if now we need to write the formulas of the multivalents? aka, so again, these are the elements that have one single charge. So these are the metals right here. Column number 1 and column number 2 are metals that have one single charge. The multivalents have multiple charges. So how do we write their chemical formula? Well, the easy part here is it's the same as before, same as non-multivalents. It's just like what we're doing right now, but this is actually easier. Only the metal charge is given as a Roman numeral. So that makes it a lot easier. We don't have to go to a periodic table to find its charge. So let's take a look at our first example then. We have tin 4 sulfide. Well, we right away know that this 4 is telling you it's the tin's charge. Tin is Sn. If it's 4, tin 4 means +4. Sulfur is S. It has a charge of -2. What's the LCM of 4 and 2? The LCM of 4 and 2 is actually 4. It's the lowest common multiple between both of them. So that means we do 1 tin and 2 sulfurs. So because of that, our chemical formula ends up being SnS2. Let's try our next example. Iron 2 oxide. Iron is Fe. It has a charge of +2. Oxygen is O. It has a charge of -2. So what is the LCM of 2 and 2? It's 2. So I just need one of each to become balanced. So what I end up getting is FeO. But what happens if I change iron's charge by 1? Now it's iron 3. By doing that, you actually change its whole chemical because its chemical formula also changes. Because now you're going to have Fe +3, and oxygen still is -2. So your LCM now is no longer 2, it's now 6. So because of that, I need 2 irons, but 3 oxygens to make them balance. So this is now going to end up being Fe2O3. That's a different chemical in itself. Alright? So now, what happens if I work and deal with polyatomics? Well, polyatomic ions are still same rules as before, but here's where it changes a bit, okay? Polyatomics are groups of atoms, are multiple atoms that are charged as a single group. And because they're charged as a single group, we write them as one unit. Okay? If more than one polyatomic ion, we put parentheses before subscript. So what this means is, for example, if we have, for example, 3 ammoniums, it will be written as NH4 3. Okay? The reason why is because if you don't put parentheses, NH4, and you put a 3, the second one looks like you have 43 hydrogens, not 3 ammoniums. Now, where are these polyatomic ions? Well, in this periodic table, it's the next 2 pages after that, after the periodic table. So these are the polyatomic ions. They have multiple charges, or they have multiple charges as well as um, they have multiple atoms, that is. Okay, so these are polyatomic ions that have multiple atoms. So these are the positive ones and these are the negative ones. Okay, so let's look at the first example. In our first example here, we have lithium phosphate. Okay, let's take a look at this. Lithium is Li. It has a charge of +1. Phosphate. Phosphate is right here. It's PO4 3 minus. So it's PO4 3 minus. So because of that, we gotta find and balance the charge. So we need to find the LCM, which ends up being 3. So I need 3 lithiums, but only 1 phosphate. And because I have just 1 phosphate, I don't need parentheses around it because we don't need to write the 1. So it becomes Li3PO4. Okay, but where's an example we do need to write its parentheses? Well, let's go to the next example. Iron 3 nitrate. Iron 3 means, again, it's iron plus 3. Nitrate is NO3. So if you look at your table, nitrate is right here. It's NO3 minus 1. So again, what's the LCM of 3 and 1? It's 3. But this time, I only need 1 iron, but 3 nitrates. Because I need 3 nitrates, oh no, I need to put a 3 outside the nitrate. I need to write it like this. Fe, NO3 in parentheses, 3. Because if I didn't have a bracket around these, then the oxygen looks like it's 33 instead of just 3 oxygens, but there's 3 nitrates here. So this is one where you have to put a bracket. Okay, let's look at our last example here, ammonium oxide. Ammonium is one of the few or the only positive polyatomic ion that we're going to work with in this class. It's NH4+. So in this case, we have NH4 plus 1. Oxide is oxygen, is O minus 1. The LCM here, or it's minus 2. The LCM here is 2. So in this case, I need 2 ammoniums, but only 1 oxide. So because of that, it becomes, again, because you have multiple polyatomic, you got to put a bracket outside of it. And 1 single oxygen outside of that. So what are some things to be careful about? The first one is, a lot of students mistaken these two elements, or these two compounds. Ammonia versus ammonium. Okay, ammonia is NH3. Ammonium is NH4+. There's a big difference. This is a compound. It's a neutral, fully exists in nature compound. Ammonium is an ion. It is different. So one's charged, one's not. Ammonia, you might find in, for example, Windex. Windex has ammonia in it. Ammonium is found in salts because an ion, if it's neutral, is usually found in salts. The other one we need to be careful about is if it's in the polyatomic ion section, which is right here, mercury 1, okay, is Hg2 2+. Now why is mercury 1 that? Mercury 1 is Hg2 plus 2. But wait, if the Roman numerals tells the charge, why is it plus 2? Well, it's because there's 2 mercuries, and if the total charge of these 2 mercuries is plus 2, then 1 single mercury is plus 1. So that's what's going on here. Okay? So let's work backwards now. Let's write the names of chemicals. Okay? So let's finish up this lesson by, first of all, let's talk about writing names. So how do you write names of chemicals? Well, to write names of chemicals, especially the non-multivalents first, first of all, metal name always comes first though. Metal name first, okay? So, what you gotta do is find name of each element from its symbol. Okay, now this is where it changes. Metal name does not change. Non-metal name ends in "ide." IDE. So how does that work? Well, let's look at a periodic table. Okay, so let's go back up to a periodic table. So we know these are the nonmetals, these are the metals. The metals name won't change in the name, but the nonmetals will. How do they change? Well, anything that's considered a nonmetal will always keep its first syllable and then add "ide" to it. So for example, oxygen is 3 syllables, but you keep the first syllable "ox" and you add the word "ide," so it becomes oxide. For example, chlorine is chloride. Phosphorus is phosphide. Now this one you keep the ph in it because it's part of that. It's kind of part of the first syllable. Um, iodide is iodine is iodide. The ones that hug the staircase, which are your semi-metals, those are the ones that keep 2 syllables and then add "ide." So for example, silicon will be silicide. Arsenic is arsenide. Selenium is selenide, right? So those are the ones that keep 2 syllables. We don't worry too much about them. We're going to worry more about the non-metals that we're going to keep 1 syllable. So let's take a look at our first example. In our first example here, we have CaCl2. Ca is calcium. Calcium's name doesn't change. Cl is chlorine. Now we don't care about the number of chlorines here because it's not we're not worrying about it too much now because it's just meant to be balanced with the charges. Cl is chlorine. Chlorine ends in "ide." It turns into chloride. SrO. Sr is strontium. Doesn't change. It's a metal. Oxygen becomes oxide. Last but not least, in this example here, Li is lithium. And again, O is oxide. So that's how we name our chemicals, our non-multivalents. But what happens if now you're dealing with the multivalents? Similar as before. But now you gotta find the metal's charge for Roman numeral. Because, for example, if I look at the periodic table here, we know that iron was +2 to +3. How do we know if it's +2 or +3 from the name? How do we know, for example, copper is +1 or +2? How do we know, for example, manganese is +2 or +4? Well, if these multivalent metals change their charge, what doesn't change its charge? The nonmetals. The nonmetals that are attached to these multivalent metals will have the same charge every single time, and that will give us a hint of what the multivalent metal's charge is. So if you, for example, have 2 fluorines, then you must know the -2 charge, or if one fluorine is -1, you have 2 fluorines, the total charge of negative is -2. So that means the metal must be +2. So we're going to use that idea to help us balance out. So find the metal's charge for Roman numeral. To do that is find total negative charge. Okay, to find that, it's the non-metal charge times by the number of nonmetals. Step 2, total negative charge equals total positive charge because it's a compound. It must be neutral. And then step 3, divide total positive charge by number of metal to find one metal's charge. Okay, so these are the 3 steps we're going to take. Let's practice these out. Okay, so we want to make sure we find that one metal's charge and put them in as a Roman numeral. So our first example is Fe2S3. Remember, iron can have multiple charges. So which iron is this? Well, we look at our nonmetal. Our nonmetal there is sulfur. We know that one sulfur has, well, if we look at a periodic table, one sulfur is part of oxygen's group. It is -2. How many sulfurs do I have? I have 3 sulfurs. So I multiply this by 3. That means my total negative charge here is -6. So this number right here is my total negative charge. Well, what must the iron be then? Well, if you look at iron, the 2 irons must have a total positive charge of +6. So this one is the total positive charge. Well, how many irons do I have here? Well, it's Fe2, so it's 2 irons. So that means if there's 2 irons, if the total charge is +6, how much does 1 iron take? We divide that by 2. And we find that 1 iron is +3. So what kind of iron is this? This is iron 3. And we end it off by writing sulfur as a non-metal name, iron 3 sulfide. Let's try with the next example, CuCl. So again, we look at our non-metal, which is chlorine. Chlorine has a charge of -1. How many chlorines do I have? I have 1. So my total negative charge is -1. This is my total negative, okay? Well, let's look at copper. There's only 1 copper. That means this copper must have a +1 charge. This is my total positive. How many coppers are present? There's only 1, so divided by 1, it's +1 still. So, this one ends up being copper 1 chloride. Our last example is another one that has to look at this. So let's look at this example here. So we look at our non-metal first, oxygen. Oxygen has a -2 charge. There's 2 oxygens, which means that in total it's -4. What's your tin's charge then? Well, there's only 1 tin. It must have a +4 charge divided by 1 for that 1 tin. So that one single tin takes on a +4 charge to balance out the oxygen. So in this case, this is tin 4 oxide. To finish up today's lesson right now, we're going to talk about the last thing here, which is how do you write polyatomic names? Well, this one's the easiest one. It's same as before, but now keep polyatomic name unchanged. What does that mean? It means do not change its ending. Okay, so don't turn it into an "ide." If it's sulfate, keep it as sulfate. Don't write it as sulfide, because that's a different chemical now. So, what do we have? Well, let's look at this first example. We have Ag3PO4. Well, let's look at our polyatomics. Silver is right here. Silver is actually one of those multivalents, so it's part of the middle section that only has 1 charge. It's only +1. But PO4, that's phosphate. So what you end up getting is you get silver, okay, silver, not a multivalent, phosphate. So silver is one of those multivalents that have only 1 charge. Okay, let's look at our next example. NH4, that's ammonium. That doesn't need to change its ending at all. S is sulfur, that's sulfide. Our last one, again, this is ammonium. Okay, but what's HCl3? Well, if you look at HCl3, where is it? It is right here. It's hydrogen carbonate, or the more common name, bicarbonate. This is ammonium bicarbonate. So hopefully you practice a lot of these type of questions. As always, make sure you keep yourself safe and healthy, and I'll see you soon.